Okay, now that my hissy fit is over, let's try and pick up where we left off. I'll try and keep that thing going. I might have knocked the stuffing out of it now. Okay, just remind me, every 10 minutes I have to get up and do something. Man, it's getting harder and harder to make videos up in this piece. Okay, C4H5N2O. All right. I skipped over 5 intentionally. The reason I did that is because it doesn't come out nice and even, and any question I put on a test is going to come out evenly. So I went ahead and did 7. And 7, first thing I do, percents to grams. Percents to grams, percents to grams, ecto, hecto. Then I do grams to moles, and I do 3 conversions there. Everybody knows how to do mole conversions, I hope. We did one up there. And then I divide by the lowest mole total. So here I got 5.45 moles. Here I got 5.45 moles. Here I got 1.81 moles. So I divided all of the mole totals by 1.818. I got 3, 3, and 1. So that is my empirical formula, C3H3O. Then, in order to find the molecular formula, when I have a molecular mass, which they've given me, 110 grams per mole, I divide the molecular formula mass by the empirical formula mass, which if I add up C3H3O is 55 grams. That gives me a factor of 2. It is molecular formula mass divided by empirical formula mass. That's a factor. That gets multiplied by all the subscripts in the empirical formula. So 2 times 3 is 6. That's C6. 2 times 3 is 6. That's H6. 2 times 1 is 2. That is O2. That is my molecular formula. And that is what they are asking for. Did the same thing for number 6. They gave me an empirical formula. They gave me a molecular mass. The molecular mass is 112 over the empirical formula mass, which carbon is 12 plus hydrogen is at 1 apiece. 4 of those is 16 grams. 112 divided by 16 is 7. So I multiply a 7 times all the coefficients, or the subscripts, sorry, not coefficients, subscripts. C7H28. 1 times 7 is 7. 4 times 7 is 28. That gives me my molecular formula. Molecular formula. Okay. Hopefully we can carry on without interruption now. Maybe. We'll see. Stoichiometry. Lovely stoichiometry. Now remember, moles to moles, 1 box. Moles to grams, or grams to moles, 2 boxes. Sorry about my ugly boxes. I'm a little flustered. Grams to grams, 3 boxes. 2 boxes, 1 box. All right, so let's see what they're asking me here. They are 6 moles of magnesium. There's my magnesium. How many moles of nitrogen are needed? Okay, so it's a moles to moles. So it is a 1 box problem. So I'm starting with 6 moles magnesium. Your units have to contain what type of material it is, or you can't do it correctly. So when you're calculating these things on the performance final, show me all your work, show me all your units. So I have moles of magnesium, and my answer is in moles of nitrogen. Remember, N2, moles of N2. And then that's the heart of my problem. This is my mole ratio, so I'm just looking to see how many moles of magnesium, 3. And how many moles of N2, 1. And that's the coefficients here, right? There's a 1 here. There's anytime we don't like to write ones, but it's there. And the 3 you can see. So 6 divided by 3 is 2 moles of N2. 2 moles of N2 for every 6 moles of Mg magnesium. Okay, now we have a moles to grams, so that is a 2 boxer. 1, 2. And we have 2 moles of nitrogen. And they're asking me how many grams of magnesium nitride I can make. Grams of Mg3N2. Be careful with this. I saw a lot of people trying to do magnesium here. You got to read. You have to read. You have to know, and then look up and go, which one of these is magnesium nitride? The one with magnesium and nitrogen in it. So grams of Mg3N2. Anytime I write grams, 1 mole of that substance on the other side. So, and then how many grams of Mg3N2 are in 1 mole? Well, I can add that up really quick. 24.3 times 3 inner plus 28 for my 2 nitrogens, so that's 100.9. And then here I have, by the diagonal rule, this has to be moles of N2. And then by the diagonal rule, this has to be moles of Mg3N2. And then it's the mole ratio, the heart of the problem. Remember, every problem is going to have a mole ratio in stoichiometry. So moles of Mg, 1, moles of N2, 1. So it seems like it's going to be 2 times 100.9, which is 201.8. 201.8 grams if 2 moles of nitrogen are used. Okay. So if 5 grams of magnesium are used, how many grams of magnesium nitride are produced? So now we got a grams to grams, so this is a 3-boxer. And we're starting out with 5 grams of magnesium. And we're going to grams of Mg3N2, grams Mg3N2. This is convenient because I know how much it weighs. I've already done that up there. Anytime I write grams, it's 1 mole on the other side. This is great because it gives me an opportunity to show you that it doesn't matter which side grams are on, right? So this is moles Mg3N2 by the diagonal rule. It has to be. That's as far as I can go backwards, so let's go forward. Here I have grams of Mg. Grams of Mg, so anytime I write grams, 1 mole of that substance over it. This must be the heart of the problem. Moles of Mg by the diagonal rule. Okay, Mg3, Mg3N2, I have 1 mole, and grams of Mg, I have 24.3 grams of Mg. Okay, now it's a math problem. So the way I'm going to do this is do 5.0 times 1 times 1 times 100.9 equals, divided by 24.3 enter, divided by 3 enter, divided by 1 enter. It looks like 6.920 grams of Mg3N2 for every 5 grams of magnesium. Yep. Okay. All right. Now we got some more conceptual questions. We like these because they're easy to do. A burning candle is placed into a glass jar. The jar is then closed. The candle burns for a few seconds before going out. However, at the end of the reaction, the candle is still present. Identify the limiting reactant. Well, in this combustion reaction, you have candle and oxygen. Those are not fire, and match are not products or reactants. We have candle and oxygen. If I put a jar over it, I'm limiting the oxygen while I have excess candle, so that is my limiting reactant. Yeah, basically the air runs out in the jar, the fire goes out. Identify the excess reactant. That would be candle, because it says I still have candle present. It's like, and I've seen this question on other tests where they drop magnesium into acid. They say that the magnesium disappears, but the acid is still present. What was my limiting reactant? Well, if the acid is still present, that ain't limiting. So it's the magnesium. All right, now we got some solubility curve questions. How many grams of KClO3 would be required to saturate 100 grams of water at 50 degrees? Well, that's easy. All of these are in 100 grams of water. So we're looking at KClO3, that's here. At 50 degrees, that's here. So it looks like 20 grams are required. How many grams of KNO3 would be required to saturate 300 grams of water at 50 degrees? Well, there's two ways we can do this. We can set this up as a proportionality, where we know that in 100 grams at 50 degrees, we can get 50 degrees KNO3, we can get 80 grams and 100 grams of water of KNO3. And then we can set 300 grams of H2O and set this to X, and we can solve it that way. Or the other thing we can do is, this is exactly 3 times the amount of water. So this is going to be exactly 3 times the amount of grams. So 3 times 80, yeah, if I'm correct, it's 240, right? Yeah, so it's just 240 grams. And you can do it either way. I don't care. It's up to you. I'm just giving you strategies for solving these things. That's one strategy. If you see it's 300 grams of water, or what if it had said 50 grams of water? Well, that's half as much as this solubility chart indicates. So if it can fit 80 at 100 grams, then it can fit 40 into 50 grams of water. It's all just a proportion. It's all just a ratio. Everything is really, really easy to talk about like that. Okay? 14, 80 grams of NaNO3 is dissolved in 100 grams of water at 40 degrees. Would it be saturated, unsaturated, or supersaturated? Well, that depends if 80 grams at 40 degrees is over, on, or under NaNO3's line. So what we're going to do is go to 40 degrees. We're going to go up to NaNO3, 40 degrees, NaNO3. And then we're going to see where 80 grams would be. 80 grams is here. So it is below the line, so this is unsaturated. This would be saturated, and way up here would be supersaturated. So 80 grams, unsaturated. What temperature is required to saturate 40 grams of KClO3? Okay, so the way we solve this is we go to the KClO3 line, we go to 40 grams, and we see what temperature it would be required to get that 40 grams. So here's 40 grams. I'm going to say that that's right in between, so I'm going to say that's 15 degrees. All right. Which of the solutes would possibly be a gas and why? Well, you'll notice that all these curves go up as we get hotter. Solubility goes up, except for one, well, two really. This guy, this is the guy we're trying to pinpoint. So NH3 is a gas. And how do I know that? Why? Because solubility goes down as temperature goes up. Coke goes flat quicker when it's hot. Don't believe me? Put a hot Coke and a cold Coke outside. Leave them for an hour. Come back and see which one has more dissolved carbon dioxide. The cold one will have more dissolved carbon dioxide. So that's page 2. Now we're up to 17. I'm going to stop the video here and do another video.